Okay, to refresh what we did on Monday, let's look at this equation. Alright, so the first thing I like to do is I like to go ahead and break up both of my reactants into their ions. Okay, then we're going to swap the positive charge of one reactant to the negative charge of the other. So that would be potassium and nitrate, and then magnesium and hydroxide. So what we'd form would be KNO3 and MgOH, and the two from magnesium swaps over. Looking at your solubility table, is potassium nitrate soluble or insoluble? Right, so it gets an aqueous behind it. What about magnesium hydroxide? Insoluble, so it forms my solid. Okay, so I always do this part first before I write it over there, because if they were both soluble, it would be no reaction. Okay, so now let's move over here. So KNO3AQ plus MgH2, and it is a solid. Okay, so we're going to add something to this. This equation that I have written here, and most chemical equations that we've come across so far, are called the molecular equations. And it's just what it sounds like. It shows all of our reactants and products in their molecular form, and it's equation. But there are two other types of equations that, if we're really just concerned with, say, the precipitation part of this reaction, these two equations that I'm about to introduce, it's more convenient, basically. Okay, so what I'm about to write is the complete ionic equation. The complete ionic equation, you break apart all strong electrolytes that are soluble What I mean by R soluble is they're going to have the AQ behind it. So for all the reactions we've done so far, anything that has an AQ behind it is a strong electrolyte. We're going to apply this to acids and bases, and that will be the case. But I'll tell you about that when we get there. So we're going to break apart everything that's a strong electrolyte that has an AQ behind it, because that's how it really exists in the solution. It's just that ion is floating around. So before I do this, let's balance it. Looks like I need a 2 here and a 2 here. Yep. Okay, so the complete ionic equation, when you have coefficients, you're going to put that coefficient with each individual ion as well. So for here, I actually have 2 potassium ions, 2 hydroxide ions. Then I move to magnesium nitrate. I only have 1 magnesium. How many nitrates do I have? 2. So I put that 2, I actually move that 2 out in front because that 2 is not part of nitrate's formula. Okay, and I continue on to the product side as well. If it has an AQ behind it, break it apart. Do not break apart your solid. So when I write the complete ionic equation, I'm not going to break apart pure solids, pure liquids, or pure gases. So I'll know that they're pure if there's an S, an L, or a G behind any of those. All right. So this looks like more work, but it shows a better representation of what I actually have going on in a container that I'm mixing these chemicals in. But there's some fluff that we could get rid of. From the reactant side to the product side, you'll notice that potassium doesn't change. In both sides, I have 2 K+ ions that are by themselves. Okay, so nothing's happening with that potassium. It's just kind of hanging out in water. Same is true with nitrate. So I'm canceling those out. These are called spectator ions. It's exactly what it sounds like. They do not change in the reaction. So in this case, Potassium and nitrate are my spectator ions. Right? So there's one last equation that I could write, and this is called the net ionic equation. The net ionic equation is just like your complete ionic equation with your spectators removed. So that's why I crossed them out. So my net ionic equation then becomes, I bring everything down that I didn't cross out. You'll notice that I put magnesium first and then hydroxide. You don't have to do that. It doesn't matter what order they go in. I just always do my positive first. So the net ionic equation is a simplified equation that tells you exactly what is undergoing a chemical change in the reaction. So for precipitation reactions, it's almost always going to be just the formation of your precipitant. Is what it'll simplify down to. Any questions on writing any of those? Okay, well let's do another. Can I erase all this? Yeah. Right, so let's predict our products of this equation, then let's write our complete ionic and our net ionic. So if you do have to predict the product, sometimes it's easier to go ahead and start your complete ionic equation. You just don't put coefficients out in front just yet because we haven't balanced the equation. But it'll still show you what ions. So those are my 4 ions. So we're going to put SR with the phosphate ion and then lithium chloride together. Lithium chloride, I know it's soluble. So let's check on strontium phosphate. I believe it's insoluble, right? Yes, I'm right. All right, so my products that I form are going to be lithium chloride. 3 SO42 solid. Now, once I have my products up there, I need to balance it before I go on and complete my net ionic coefficient. So, looks like I need a 3 here. Phosphate has a 2, so I need a 2 there, which means I need a 6 here. So now I've got to go in and add a coefficient in front of these ions. So it'd be 3 here. For chlorine, it'd be 3 times 2, so it'd be 6 right there. 6 for lithium, 2 for phosphate. Now I can do my products. I'm going to break lithium chloride up. This is aqueous. Then I keep my solid together. Okay, there is my complete ionic. Who are my spectators? Yep. I'm going to cross those out. So then bring down everything you didn't cross out. And again, my net ionic equation just ends up being the formation of my precipitate. We good here? Pretty good? Yes.
Wait, why was Chongqing not be spectator? Isn't it just one?
Who? Strong?
Yes.
Because it changes from that side to that side. It's involved in making your solid.
Oh, okay.
Anything else? Alright, let me give you one to attempt, and then we'll move on. Alright, so I'm going to let you attempt this one, predict your products, and then write complete and net ionic, then I'll work it out with you. Alright, let's look at CR. Alright, NABR. Why can I not find a good document? NABR is soluble. You'll get that for your products. And it needs to be balanced. You just need a 2 in front of the NABR. Then we can start our complete ionic. Okay. There's our complete ionic. And my spectators are who? Correct. Then I bring down what is left. And I again just get the 2 ions that form my solid. Good. Alright, now we're going to talk about acid and base reactions, but we're going to apply all of this to those. Eventually, it might not be today. There are several definitions of acids, but I think the only one we'll consider right now is when it's dissolved in water, it's going to produce an H+ ion. An example is HCl. If I have aqueous behind it, that's the same as saying I have water present. Okay, so when this dissociates, it breaks up into a hydrogen ion and the chlorine ion. So this is an acid. Another way you might see it written is where you actually add the water. And when you go to the product side, instead of this H plus just floating around by itself, it actually combines with water to form what is called the hydronium ion, H3O plus. So this is the hydronium ion. You will see hydrogen by itself and H3O plus used interchangeably. I can try to spell that today. So hydrogen and the hydronium ion, it's the same thing. I like this chapter because it's a little bit of everything. So like if you're tired of math, well, we did a little math, but we went on to something else. If you're tired of that now, we're about to do something else. When we were naming compounds, we didn't talk about naming acids. So we actually have to learn how to do that in this chapter. Can I erase all this? Okay. Right, so we're going to divide acids into two categories. The first will be binary acids. This is just going to be hydrogen and a nonmetal. Usually one of your halogens, but not always. Alright, so here's some examples of some binary acids. It's all hydrogen bound to some nonmetal. You'll notice too that I included the aqueous abbreviation behind each of these. The reason I did that is because if that AQ was not there, you would name these according to the rules we learned in chapter 4. Like, for example, this would be hydrogen fluoride, hydrogen chloride, etc. But when you put that AQ behind it, it is now acting as an acid. So to name them, you use the prefix hydro, to name it, we're going to use the hydro prefix attached to the root name of our nonmetal with IC as a suffix followed by the word acid. I know that sounds like a lot. It's really not. Right, so this first one would be hydrochloric acid. So I use the hydro prefix, the root name of my nonmetal followed by IC, followed by the word acid. The next one would be hydrochloric. Hydrobromic. Hydroiodic. And then the last that I have up here would be hydrosulfuric. So binary acids, pretty straightforward. The other acids, they're called oxyacids. Oxyacids are going to be hydrogen and a polyatomic ion. Y'all's favorites. The biggest difference between binary acids and oxyacids as far as naming goes is with oxyacids you never use the prefix hydro. Instead. Instead, what you do is you change the ending of your polyatomic ion's name. So if it's sulfate, for example, that ends in ATE. I change that to IC and add the word acid. So instead of sulfate, it becomes sulfuric acid. No hydro. So sulfuric acid, hydrosulfuric acid, two very different acids. So that's what sulfuric acid looks like. It's actually H2SO4. There's 2 hydrogens because sulfate has a 2- charge. So I still just swapped and dropped my charges. Another good example is phosphate. Phosphate has a 3- charge. So the formula for phosphoric acid is H3PO4. Any questions here? It just requires practice. Can I erase? I'm going to do a couple more examples real quick. Most of the time, even with your oxy acids, it's routine to write the AQ behind it. And then sometimes it's not there. Okay, so number 1, it's HClO3. ClO3 is the chlorate ion. So it ends in 8, so I'm going to change that to IC, azoric acid, chloric acid. Again, that's very different from hydrochloric acid. Anybody know what this polyatomic ion is? So it's acetic acid. Here, this is a derivative of phosphate, but it's 1 less oxygen, so it's what? Phosphite. So we changed the ending to OUS instead of IC. So it's phosphorus acid. And number 4, what y'all think? Nitric acid. Because NO3 is the nitrate ion. This, number 5. So all of my other polyatomic ions contain an oxygen, which is why they're called oxyacids. This polyatomic ion does not. So we actually named this based on the binary acid rules. So it's hydrocyanic acid. If I remember correctly, that's the only polyatomic ion that was on y'all's chart that didn't have oxygen, so that's the only one that applies to. Lastly, I have a derivative of chromate. So, but it has one more oxygen than chromate, right? So this would be the perchromate ion. So this acid would be perchromic acid. So that's naming acids. You already know how to name bases. Bases, I won't rush through that, never mind. I'll talk about that on Friday. And then we'll talk about their reactions. Thanks for coming. See y'all soon.